Hey everyone, and welcome to today's Explainer. We're tackling a topic today of absolutely mind-bending proportions. We aren't just looking at the present right now. We aren't even looking at the distant future of our own planet or our solar system. We are embarking on a journey to the very edge of existence itself, to understand the ultimate thermodynamic fate of our cosmos. It's an awe-inspiring, massive scale. We're talking about timelines that literally make the entire history of the Earth look like a fraction of a millisecond. But hey, don't worry, we're going to break it all down clearly, step by step, and make the unimaginable completely accessible.
So, how does the universe end? It's the ultimate existential question, isn't it? Humanity has been looking up at the stars for millennia, wondering where it all came from. We've built massive telescopes, we've collided particles, all to understand our cosmic origins. But perhaps even more terrifying and profoundly fascinating is the question of where it's all going. How does the grand play of the cosmos actually end? Does it crash back in on itself, or does it just slowly fade away? Well, today, we're going to look at the exact physics and mathematics that answer that very question.
Okay, let's dive right into this. To really understand the end of the universe, we actually have to start with something incredibly mundane. Imagine a steaming hot cup of coffee sitting right there on your desk. If you just leave that coffee alone, what happens? The heat doesn't stay trapped inside the cup forever, right? It disperses. It slowly, inevitably spreads out into the colder room until the coffee and the air around it reach the exact same temperature. This simple, everyday occurrence is actually the second law of thermodynamics in action. It's an inescapable rule of physics telling us that energy always tends to spread out. It never naturally concentrates.
And that brings us to the ultimate villain of our cosmic story, entropy. Entropy is basically just the measure of that disorder or energy dispersion in a system. You can think of the entire universe as a giant, magnificent, perfectly wound clock. From the very moment of the Big Bang, that clock was tightly coiled, packed with highly ordered energy. And ever since that initial spark, the clock has been ticking, slowly and inevitably winding down, as energy spreads further and further apart across the expanding void. Entropy is the underlying director of the whole cosmic play, and it dictates that everything, absolutely everything, must eventually wind down.
So here's our roadmap for this journey. We'll start with the engine of entropy, then move through the era of stars, journey into the dark black hole era, arrive at the final equilibrium, and end on something truly astonishing, what we call the mathematical miracle.
All right, Section 1, the engine of entropy, the rules of reality.
To give our explainer the proper academic weight here, consider the Boltzmann entropy formula. Now, this isn't just any equation. This is so profound and so central to our fundamental understanding of physics that it's famously carved directly onto the tombstone of the brilliant 19th century physicist Ludwig Boltzmann. In this formula, S represents entropy itself, the K is the Boltzmann constant, and W represents the number of microstates, or basically the different possible ways energy can be arranged in a system. Put simply, it's the mathematical proof that disorder is overwhelmingly more likely than order. Think about it. There are infinite ways for a glass to be shattered, but only one way for it to be perfectly intact.
And this brilliantly illustrates why our universe looks the way it does right now. You might be wondering, if entropy is constantly pushing things apart and demanding that energy spread out, why do we have distinct orderly things at all? Why do we have blazing stars, complex planets, and highly organized human beings? The answer is gravity. Gravity is the hero fighting entropy. It pulls matter together, aggressively clumping loose gas and dust until the pressure is so intense that stars ignite and galaxies form. But we have to realize that these are just temporary pockets of low entropy. Gravity is putting up a valiant fight, holding the universe together. But as we'll see, it's a fight that it ultimately cannot win.
Moving on to Section 2, the era of stars, also known as the stelliferous era.
Let's see how this timeline builds. Right now, we live in the stelliferous era. It's an era defined by stars, full of abundant light, complex biological life, and immense temperature gradients. That just means the vast, energetic difference between a blazing hot star and the freezing cold vacuum of space. But this is just a fleeting, almost infinitesimally brief moment. The stelliferous era is going to give way to the degenerate era in trillions of years, and then we make a massive, exponential jump to the black hole era. We are truly just in the very early, bright morning of the universe's lifespan.
So, how does our current era end? Honestly, it's simply a matter of running out of fuel. The universe currently thrives on nuclear fusion, but eventually, galaxies will completely exhaust their sprawling clouds of star-building gas. When that happens, no new stars can be born. Imagine the night sky, a vibrant canvas of billions of lights, slowly turning off over eons. Stars will extinguish one by one. Now, the longest living stars in our universe are red dwarfs. They burn their fuel incredibly slowly, barely at a simmer compared to our sun, and they can last for trillions of years. But even they aren't infinite. Eventually, the very last red dwarf will fade away, its embers cooling into a black dwarf, and the universe will go entirely dark.
Section 3. The Black Hole Era. Welcome to the Cosmic Graveyard.
First, we pass through the degenerate era. At this point, the only things left are stellar corpses, white dwarfs, incredibly dense neutron stars, and black holes, silently drifting through the absolute dark. But it gets even bleaker. Theoretical physics introduces a concept called proton decay. This suggests that over unfathomable stretches of time, protons, the very foundational building blocks of all matter, will simply fall apart. If proton decay is real, it means no solid matter is permanent. Even the dead, cold space rocks, the frozen planets, and the diamondized cores of dead stars will eventually dissolve and evaporate into pure radiation. Literally, nothing tangible remains.
Which leaves us with this number: 10 to the power of 100 years. That's a 1 followed by 100 zeros. It's called a googol, a timeline so vast, so deeply expansive, it totally breaks human imagination. There aren't even that many atoms in the entire observable universe. We are now incredibly deep in the black hole era. All the stars are dead. All the planets have evaporated into radiation. For this incomprehensible stretch of time, black holes are the only living things left, endlessly roaming the completely dark, expanding universe.
But here's the thing. Even black holes cannot escape the iron grip of entropy. Through a process called Hawking radiation, discovered by the brilliant Stephen Hawking, a black hole slowly leaks energy out into the void. It's an agonizingly slow process, but it happens. Step 1. The black hole radiates away a tiny fraction of its mass. Step 2. Surprisingly, as its mass decreases, its temperature and power output actually increase. It starts to shrink faster and faster, getting hotter and more volatile. Until Step 3. The very last black holes in the universe evaporate in a sudden, spectacular final flash of light. A final firework in a dead cosmos.
All right, Section 4, the final equilibrium, the big freeze.
This stage brings us to the ultimate end, the final blackout. The last black hole is gone. Maximum entropy has finally been reached. The energy of the universe is completely, perfectly, evenly spread out across an unimaginably vast expanse. There is perfect balance, meaning there are absolutely zero temperature differences anywhere. And remember our coffee cup analogy from the beginning? Without a difference in temperature, energy cannot flow from a hot place to a cold place. Without energy flowing, no thermodynamic work can be done, no information can be processed, and therefore no life, of any conceivable kind, can exist.
So, the really crucial point here is this. This is not just the end of matter, it is the end of time itself. Seriously, think about it. We only perceive time because things change. Particles move, planets orbit around stars, a biological heart beats, a clock ticks. But in the big freeze, at maximum entropy, perfect equilibrium dictates that absolutely nothing will ever happen again. Not ever. Because literally nothing changes, the very concept of time ceases to have any meaning. There's no past, present, or future when the universe just rests in a state of eternal, unchanging nothingness.
Section 5. The mathematical miracle. Let's talk about the so what factor.
Now, what's really interesting here, and I know all of this sounds incredibly bleak, is a bizarre concept known as the Boltzmann brain paradox. Physicists note that in an infinite timeline of endless random energetic fluctuations, even in a dead, frozen universe, matter might randomly clump together again purely by chance. But mathematically speaking, the likelihood of a single conscious brain spontaneously popping into existence out of the empty void, fully formed with false memories, is actually astronomically higher than an entire complex organic galaxy forming the way ours did. This paradox highlights just how absurd, complex, and deeply improbable the reality we live in right now actually is. It makes you realize how utterly fragile a structured universe truly is.
And that leaves us with our final thought for today's explainer. Yes, the second law of thermodynamics dictates that our universe will eventually end in a vast, dark, timeless equilibrium. But look around you. Take a deep breath. We exist in a fleeting, miraculously highly ordered pocket of low entropy. We have stars that warm us, planets that harbor oceans, and a universe teeming with activity. More importantly, we have consciousness.
Knowing how the universe will eventually fade away into a dark freeze, isn't it an absolute mathematical miracle that we are here, right now, with the ability to look up, calculate the cosmos, and witness its incredible beauty? Take that thought with you today. Until next time, keep exploring.